We have two great ideas, the derivative and the integral, and they are about to turn out to be one. Start with a curve, fix a left edge, and let the right edge slide. At each position, measure the area collected so far from the fixed start out to the moving end. That running area is itself a function. Call it the area so far. As the right edge moves along, the area grows, and we plot how much we have gathered. The top curve is the original. The bottom curve is the area beneath it, drawn as it accumulates.
So the bottom graph is a brand new function, built entirely out of area.
Exactly, and now we ask the question that unlocks everything. How fast does that area function grow? Nudge the right edge forward by a tiny step. The area gains one thin strip. Its width is that tiny step, and its height is just the value of the curve right there. So the extra area is the height of the curve times the tiny step. Divide the extra area by the tiny step, and you get the height of the curve. That is exactly a rate of change. And that is the first half of the theorem. The rate at which the area grows is the height of the original curve. In other words, take an accumulation and differentiate it, and the original rate comes straight back. The slope of the area function is the curve you started with. Accumulating and differentiating undo each other. The first half hands us a gift, the shortcut we suspected last episode. To find the area under a curve, do not sum 1,000 slices. Instead, find a function whose rate of change is that curve, an antiderivative. Then the exact area from the start to the end is just that function at the end, minus its value at the start. A difference of two numbers, in place of an endless sum. That is the second half, the evaluation rule, and it is what makes integrals actually computable. Every time you work out an area, or solve for a total, this is the machinery underneath. The suspicion from last episode is now earned. Step back and look at the shape of it. The derivative takes a total and gives you its rate. The integral takes a rate and gives you back the total. They are inverse operations, like adding and subtracting, or multiplying and dividing. Do one, then the other, and you return to exactly where you began. This is why calculus holds together as a single subject, rather than two. Episode 2 studied the rate. Episode 4 studied the total. The fundamental theorem says they were always the same object, seen from two directions.
So the hard part, the infinite sum, gets replaced by running the derivative backward.
That is the whole trick, and it is why the subject is usable at all. So the fundamental theorem, in two halves. Differentiate an accumulation, and the original curve returns. And to integrate, run a derivative backward and take a difference. There is a bonus hiding here. Because composed rates multiply from the chain rule episode, integrals can undo a composition too by a move called substitution. Reverse the chain rule, and hard integrals come apart. Everything so far has lived on a single line, one input, one output. Next, we let the world have many directions at once, and the slope becomes a gradient. That is calculus in many dimensions,